So, we started with the topic on ferroelectric domains after we completed first and second order transition. So, as we discussed, ferroelectric domains are actually regions of uniform polarization. So, that is one of the essential characteristics. And these domains do not translate all over the region of the crystal. Of course, it depends upon the size of the crystal, but for a normal ceramic or single crystal, you never have a state which is monodomain state, means whole material is not in single domain state, and that is because of as we discussed last time, when the domain gets bigger, since you have polarization in the material, so you have state like this. Now, this is a monodomain state. If you have a monodomain state, then you have build-up charges on the faces of the crystal, and this gives rise to large electrostatic energy, which results in large depolarizing field. So, this depolarizing field wants to tilt this polarization vector in the opposite direction. Okay. So, there is a depolarization in a field or energy, electrostatic energy, which favors reorientation of this moment or dipole moment into other direction, which means it wants to break into multi-domain state. So, for instance, in a state like this, so here it translates itself into two states. So, the net charge density on the faces of the crystals goes down as a result of formation of two domains. So, now you have here you have single domain, and here you have multiple domains. Now, but at the same time, you also see when you make a domain, it comes with itself with a surface. So, this interface between two domains, which is called as domain wall, this is actually a surface, a physical surface. Now, as long as it is a physical surface, it requires energy. So, that energy now is a positive energy, it is a requirement. So, we need to find a balance between. So, basically, it depends, the size of the domain will depend upon balance between electrostatic energy which is due to depolarizing field and domain wall energy, which is the surface energy. So, what we will do a little later in this lecture is we will just find a balance between these two energies in order to find the optimum domain size that we will obtain. So, this would reduce the energy of the system. So, this reduces the energy, this increases the energy. So, we need to find a balance between these two. Now, domain walls in the crystals. So, for example, you start from a cubic state of a material. This is paraelectric state. So, when you cool it, so cool below Tc. So, this is paraelectric high temperature state, which is above the Curie temperature, okay, above Tc. Okay. Now, when you cool it below Tc, then the material transforms into tetragonal. So, what you have is a tetragonal face. So, here it is AC, AC, here it becomes AT and CT. So, that is how tetragonal crystals are defined. Now, in a tetragonal crystal, this would appear as if you have formation of polarization along this direction, which means build up of charges on the faces, and corresponding to this PD you will have what is called as depolarizing field. Just a second, let me just make a distinction here. This is PS. So, corresponding to this you will have a depolarizing field, which is corresponded by PD or let us say ED. Okay. Now, this ED makes this monodomain state unstable. As a result, what happens is this crystal breaks itself into two parts. So, this is PS in this direction, this is PS in this direction, and hence the surface charge density goes down, and as a result the depolarizing field gets equal to 0, but you form an interface. Now, this could also happen by application of stress below Tc. So, you take a cubic state, go to below Tc, and then you apply stress. And you apply stress. So, for instance, you had a situation like this. You have a tetragonal state At and Ct, followed by this Ps, which is the polarization vector. This is so the previous scenario is same as saying at the temperatures below Tc, you apply a stress sigma here, and when you apply the stress on the faces of the crystal, this converts into something like this. So, you have a polarization vector in this direction, Ps, another polarization vector in this direction, and this gives rise to, so this would be Ct, this would be At, and this would be Ct, this would be At. So, now you can see the wall is not 180 degree, rather you have a 90 degree domain wall, and this 90 degree domain wall. So, you can have variety of these domain walls. You can have domain walls of 90 degree and 180 degree. You can also have domain walls of the order of 71 degree and 109 degrees. Now, the angle of the domain wall that you will get in a given crystal will depend upon the crystal structure. So, for instance, a tetragonal material or tetragonal structured material such as barium titanate or lead titanate in the ferroelectric state will have 90 degree or 180 degree domain walls, whereas something like PbZrTiO3, PZT, which is commonly known as, it will have in the rhombohedral form in the ferroelectric state. It will have polarization along 180 degree, it will have 70 degree domain walls along 180 degree domain walls, 71 degree domain walls, and 109 degree walls. So, the orientation of domain wall is determined by the crystal structure of the material. So, that is one of the domain wall is related to crystal structure of the material in the ferroelectric state. Now, that we just mentioned was, do not confuse this domain wall as a grain boundary for the reasons which I will explain now. Suppose you have a crystal like this. Okay. All right. Now, let us say in this crystal, so this is your, so these are hypothetical lattice points. Okay. Now, in the ferroelectric state, so this is the center of these unit cell. So, the central atom will sit at these places in the ferroelectric state, in the non-ferroelectric state. In the ferroelectric state, let us say these atoms are shifted here. So, this is the direction of Ps. Okay. Now, this is a monodomain state. Now, when you form what happens in a 180 degree domain wall is simply, so this is domain, let us say this remains as domain 1. Now, the other part of the crystal converts into domain 2 with a 180 degree domain wall. So, what essentially it will mean is that this guy which is here will move here. and so this would convert into domain 2, and this wall region will be 180-degree domain wall. So, you can see that there is no change in the crystal structure, there is no change in the symmetry at the domain wall. It is just that across the domain wall the orientation of polarization has changed. So, there is a little bit of shift of the central let us say titanium atom in barium titanate along the direction of along C axis. So, this would be your C axis along C axis in case of a tetragonal crystal. So, there is no discontinuity here, unlike what you find in a grain boundary. So, this is one of the major differences in terms of grain boundary in terms of distinguishing domain wall with a grain boundary. Similarly, you can draw the same picture for a 90-degree domain wall. Typically, what you see is that these 180-degree domain walls would be about a unit cell or thick. So, this is an ideal picture, but what the picture would look like in reality is something like this. So, you draw another unit cell across it, because here there is an abrupt change in the PS vector. Now, that is something which is which intuitively you do not expect, and this does not happen mathematically as well. So, what happens physically is essentially you have this atom in this domain in this direction, and the central region, which is this region, is typically you will have this atom sitting at these places approximately at the center. So, there is a gradual transition from one domain to another. You have plus PS in this direction, you have this becomes minus PS. So, PS changes from up to down gradually, and this region is now domain 2, and this becomes domain wall. So, domain wall is typically an unit cell thick. So, this is very small number, this you are talking in terms of angstroms, whereas domains typically of the order of few tens of nanometers in the ferroelectric, tens or even hundreds of nanometers depending upon the structure of the material, what form of material is it in, whether it is in polycrystalline state, whether it is in single crystal state. Domain wall is governed by those factors as well. Similarly, you can draw this atomistic structure for a 90-degree domain wall as well, which I will leave it to you to verify yourself that how it looks like. Now, how does the question now is, how does a domain wall look like? The domain wall looks like something like this. I'll show you a view graph here. So, if you look at this slide show, so this is a structure of a domain wall in a ferroelectric material. This is a picture of barium titanate. So, this is in barium titanate single crystal and or polycrystalline material, I think, and in this you see under transmission electron microscope. So, this is a TM image. You can see that the microscope, the image bar is here about, so this much length is about 1 micron. So, this whole image is roughly 2.5 microns or 2 microns wide, and in these regions, as you can see these stripes here, these stripes are nothing but individual domains, and these are nothing but your so you can see, you can observe these domains under microscope. You can look at single crystals in optical microscopes just by doing some polarized light microscopy. You can do transmission electron microscopy, because you get some strain contrast, you get this domain contrast, which helps you visualizing the domains of very fine size even under equipment like transmission electron microscope. So, this is what is and this image, by the way, was taken from Do-It-Pom's package of University of Cambridge, UK. So, you can go to that website, Do-It-Pom's, and do the Google search Do-It-Pom's microscope library and just look at these images which are provided on the website. And another thing that you need to remember is, take the case of barium titanate or lead titanate. Now, since this is a tetragonal material, it has 180-degree domains and it has 90-degree domains. Now, these 180-degree domains, 90-degree domains, both of them are instrumental both of them contribute towards reduction in the energy which is due to depolarizing field which opposes the spontaneous polarization. However, elastic energy is minimized only by 90-degree domains. So, even though you have two kinds of domains present here, 180-degree may be more common, but although both of them are present in variety of crystal structures, both of them make different contributions to the energetics in the structure. So, so basically the driving force, now we are slowly moving towards the thermodynamics. So, basically the driving force towards the formation of domain wall or of a domain wall, and which gives rise to multiple domain states, is because of minimization of electrostatic energy of the depolarizing field, which is called as ED, and this is because of surface charges which are created due to spontaneous polarization, and also minimization of the elastic energy due to mechanical constraints. And this is typically due to ferroelectric to paraelectric phase transition. So, you can because you change the structure from cubic state to tetragonal state, there is a change in the lattice parameter, and this change in lattice parameter gives rise to stresses, and these stresses or mechanical constraint lead to formation of typically 90-degree domain walls. So, elastic energy of the system is minimized by the creation of domain walls, which help in minimizing this kind of energy. And so, this basically so this electrostatic part is dealt with So, electrostatic part of energy minimization is basically splitting of a single domain into multiple domains of opposite orientation. While compensating energy is the surface energy. Okay. So, this is what you need to remember. Now, what we are going to do is that we are going to do an analytical treatment in order to find out what is the optimum domain size that we get when such forces are present there. So, as we know that ferroelectric domains form because of instability of dipoles to be aligned in one direction. Since monodomain is not a stable state, you have a multiple domain state. As a result, you have this multiple ferroelectric domain. Now, when you have such kind of situation, when you have on one hand electrostatic energy, another hand you have surface energy and various other energies involved, overall the system will have a free energy. When you go from a single domain state to multiple domain state, this free energy must reduce in order to make this multi-domain structure as a stable structure. So, this free energy, the free energy change So, let us just write this heading here. Analytical treatment. So, this delta G, which is the free energy change involved in the formation of a domain, is given as, or formation of domains is given as delta G, which is G minus G naught, and this is nothing but sum of various kind of energies. You can have UC, another is UP. So, UC is nothing but the effect of applied field on domain energy. So, field there is a field dependence to it as well. Then you have a term called as UP and UX, and these UP and UX are bulk, electrical and elastic energies. And then you have what is called as UW, and then you have another final term which is called as UD, and UW is the domain energy, and UD is the depolarization energy. Which is basically due to depolarization field. So, now here the first three terms are effectively neglected because in the minimization of free energy, because these three terms do not have significant influence on the domain size because elastic and electrical energy are virtually constant, or they can be assumed to be constant for simplicity of treatment. And if you make the electric field constant, then this effect also is neglected. So, we can now what we have to do is that in order to get a stable domain energy domain structure, we need to minimize this delta G, and when you have this minimization of delta G, it has to be done with respect to a given domain size. So, when you do this delta G, del of delta G by del of, let us say, domain wall size is called as delta. So, del of delta G is equal to 0, and in this process we neglect these terms, assuming these to be independent of domain size, and which is a fairly good approximation, because it turns out that all these three parameters do not show an appreciable effect with respect to the domain size. So, the first thing now we need to know is that the UD, let us say, and this UD is the depolarizing energy. So, what essentially it means is that this free energy curve, when you, for instance, this is your delta G and this is your delta. So, this with respect to this delta, this free energy curve has to show a minima somewhere, and this delta is the optimum delta that you need to find. So, basically at this point, this del of delta G versus del delta has to be equal to 0, and for that we need to know, which means that UW and UD have some dependence on the domain size, and that is what we are going to look at. So, let us say the domain size is delta, and this UD is basically related to the internal energy which is set up by this depolarizing energy, and this basically internal field opposes the applied field, and hence it's called as a depolarizing field. So, this UD essentially is given as epsilon star delta V P naught square divided by T. Here epsilon star is essentially dielectric constant, related parameter, V is the volume, P naught is the polarization at the center of the domain, and T is the crystal thickness. So, this is your depolarizing energy term. Now, we need to find out what is the other term, and this other term is UW, which is the domain energy, and this domain energy UW can be expressed as gamma divided by delta into V, where gamma is the surface energy of domain wall, V is the volume again, and delta is the domain width or size. Okay. Now, we have taken since UP and UX as constant because they are fairly constant in each domain, and UC is something which is also, when you take constant field, then it's again a independent quantity of delta. So, we can make this whole thing equal to, they remain constant. So, as a result, when you differentiate delta G expression, they go equal to 0. So, what you do now is that we just minimize this energy with respect to delta. So, what you need to do now is, so now we need to, we are taking del of delta G versus del of delta is equal to 0. So, as a result, now this becomes basically del of delta G, del of delta is essentially of UD plus UW. And if you look at these parameters here, so what you have here is epsilon star delta V P naught square, epsilon star delta V P naught square divided by T plus you have gamma V divided by delta, and this is equal to 0. So, essentially the first term becomes epsilon star V P naught square divided by T, and this other term becomes minus of gamma V divided by delta naught square, and this is equal to 0. So, of course, V goes out. So, what you have here is delta naught square is to be equal to gamma T divided by epsilon star P naught square, and which means delta domain width delta is given as root of gamma T divided by epsilon star P naught square. So, this is what is the equilibrium domain wall width, which leads to minimization of free energy, and as you can see in this expression, you have dependence upon the polarization. So, which means larger the polarization is, smaller the domain size is going to be, and that kind of makes sense because larger the polarization is, larger the depolarizing field will be, and more will be the driving force towards formation of domains. So, this increase in any increase in P naught, and this goes as square as well. So, there is a pronounced effect of polarization on the domain size, and then there is the effect of gamma, which is the surface energy on the polarization. So, as the domain wall energy goes up, delta also goes up because you want to minimize the number of domain walls, which lead to basically increase in the requirement. So, this is the expression. So, basically as gamma increases, delta increases, which means and as P naught increases, delta decreases. So, you can see this conflicting requirement, and that is what leads to balance of situation resulting in equilibrium domain size. Okay. And this domain, so we have gone through the concept of domain wall. Now, this domain wall has a concept of this domain wall has a significant influence in the way we explain this ferroelectric hysteresis loop. So, now when you draw a ferroelectric hysteresis loop, so you start polarizing from this point. This is the virgin state of the material. In the virgin state, all the domains are randomly distributed to each other. As a result, the net polarization is equal to 0 because material has never been poled. And when you start polarizing it, it increases little bit linearly in the beginning, and then it becomes a nonlinear process, and then you reach what is called a saturation point, and when you reach saturation point and then you come back, it goes back to remnant polarization, and then the cycle starts. So, this is what it is going to be like. This is going to be your saturation polarization, this is your remnant polarization PR, again minus PS, minus PR, and these are called as we know coercive fields EC and minus EC, and this is polarization axis and this is electric field axis. So, here in this state the domain structure of a material would be, you have this is the grain size and these are domains, and in the domains you will have random distribution of domains. So, this gives rise to P equal to 0, this is called as this is in the virgin state, which means as made material. But the moment you start pulling it, you have formation of new domains. Now, this does not happen like in, as we will see in magnetic material. In this case, here in ferroelectric materials, each time when you do the polarization, it is always the nucleation and growth of new domains rather than. So, you might think that that these energies, these domains which are favorably oriented would go in the direction of applied field, but no, this process is more energy consuming in ferroelectric materials than the nucleation and growth. So, what happens is that at the boundaries of these domains, or the boundary of grain boundaries and various kind of surfaces, which, and as you know from the phase transformation fundamentals, that when the nucleation and growth process happens, because of energetic regions, nucleation prefers to take place on foreign surfaces, which minimize the energy requirement for a critical size to grow, and the critical size can also be smaller in case of foreign surfaces. So, what happens is that these domains, new domains start growing in the direction of applied field. So, what you will have, for instance, at this point is, if you look at a material, so you have this structure. So, what will happen if you look at here now? So, let us say the field direction is this, then new domains will start growing like this. If this is the grain boundary, the new domains will start growing. Okay. And these new domains are oriented in the direction of applied field, and as they grow, they consume all the domains which are unfavorably or otherwise oriented. So, what you have as a state, for instance, at this somewhere at this position is, let us say this is the structure. So, you have these domains which are formed in the direction of applied field, bigger domains. So, these are the favorably oriented domains, and the other domains, the basically the fraction of other domains are decreased and the fraction of favorably oriented domains are increased. And when you reach PS, then all the materials, across the whole volume of the material, you might have these are the grain boundaries, and everything will be single domain. So, this is your single domain state. So, basically you have all the domains show single orientation of dipoles. When you get back to this situation, what happens is that at this point, so again this is the grain boundary, and so what happens is that when you come to this point, most of these domains remain in this orientation itself, but some of the domains revert back to other orientations. So, as a result, there is a net P which is not equal to 0, because you have some domains which are favorably oriented left in the material. In order to bring these domains back to the volume of oppositely oriented domains, you need to take the material to another field in negative direction. So, that here basically the fraction of favorably oriented domains is equal to unfavorably oriented domains. So, basically all the polar vectors in all the domains cancel each other. So, this results in P is equal to 0, and then when you go back to this situation, when you further decrease the field in opposite direction, then the same thing happens which happened in the when we increase the field in the positive direction, and this basically gives rise to a hysteresis loop, which basically the area under the hysteresis loop is the energy which is dissipated in this process, or energy which is consumed in this process of domain reversal. And what you get at 0 field is two stable states of polarization which has plus and minus PR, and this is what is the crux of ferroelectric. Not only ferroelectric material, as we discussed earlier, is a non-centrosymmetric material, has a unique polar axis, but the unique polar axis can also be reversible. So, you have plus a state, plus PR state and minus PR state, and this is what makes a ferroelectric extremely useful from the fundamental from the application point of view. I will show you one animation for this domain wall reversal, how it takes place in the materials. And if you just bear with me for a couple of moments, let me just find out. So, essentially what you have is basically a material here which has which we start at this point, which is fully polarized, and this sample is sandwiched between two electrodes which facilitate the application of electric field. Now, the electric field direction is shown by this red arrow. Now, we start the animation now. So, we go from this state to other state, which is taking, if you look at this red ball, it is moving towards the left, which means we are decreasing the strength of applied electric field. Now, what you see here is, as a result of application of this electric field, you have nucleation of these domains at the interface between the sample and the electrode, and this interface is because it is a foreign surface and it helps the nucleation of new domains, simply because if you go through nucleation and growth fundamentals, you will find that foreign surfaces assist the nucleation. So, formation of new favorably oriented domains take place in this direction. Now, these domains are oppositely oriented because you have because you are decreasing the strength of applied field, or which is to say that you are taking the field in other direction. So, the new domains will have orientation in the opposite direction as to direction of applied field. So, this is just below the saturation polarization, you have little bit formation of domains, and then what happens is that this is when you reach 0 electric field. So, what happens at this point is new domains which have formed as a result of reduction in applied field, they have grown larger in the extent. As a result, they sweep out or they completely eliminate the overall polarization. So, what happens is basically the polarization due to these black arrows and polarization due to red arrows, they cancel each other, and hence you have they don't completely cancel each other at this point. So, they basically so these red arrows cancel the polarization which is equivalent to this volume itself. So, but if you look at this image, the volume of material which is occupied by black arrows is larger than the red arrows, which basically shows that you still have some polarization left in the material, and this is what represents your plus PR state. And now, when you take the field further back to opposite direction, which means you have gone below 0 now. Now, here these domains have further started growing, they have become bigger, the polarization is still finite because the black arrows are still reasonably large in number, and when you reach this point EC or minus EC here, the domains of red arrow are equal in size in comparison to domains of black arrows. So, this is where the polarization becomes equal to 0, and then when you start the process again, and this field is basically called as coercive field, and when you take this field further stronger in another direction, you go to so here look we go basically all the way to saturation. So, here you can see that these red arrows have become stronger and stronger, and the black arrows, the area occupied by black arrows has become smaller and smaller. So, as a result, when you go to this switching field, which is the field at which saturation occurs, you reach the complete reversal of polarization. So, this is the minus PS state. So, this animation sort of helps you in understanding how the domains nucleate and how does the polarization change from plus PS to minus PS going through plus PR and 0 PR states, and the same thing will happen when you go from here to minus PS to plus PS, so which is identical. So, this hysteresis curve is symmetric with respect to both the axes. So, as a result you have plus PR and minus PR and plus EC and minus EC. Any shift in the hysteresis curve is because of extraneous regions, not because the ferroelectric has that. So, ferroelectric intrinsically has this hysteresis loop which is symmetric with respect to both the axes. Okay. So, I hope this animation helps you understand the basically objectives of this. So, just let me go again. You have a virgin state, you start nucleating new domains, then you get a monodomain state. When you get a monodomain state, from here PS to PR, not all the domains remain in that orientation. What happens is that you form the new domains with opposite orientation, and this new domains with opposite orientation result in decrease in the polarization, but you still have finite polarization, and then the whole process goes through P is equal to 0, because the volume or area of oppositely oriented domains is equal to volume of other orientation. So, plus and minus PS cancel each other. So, and when you go to switching field, which is the field at which the saturation occurs, then all the domains have oriented in other direction. So, as a result you get minus PS. So, this is what is the domain formation and domain reversal under the applied field when you switch a ferroelectric material. And these quantities you must remember: PS is called as saturation polarization, PR in the ferroelectric terminology is called as remanent polarization, EC is called as coercive field. Okay. And the units you can see, this would be microcoulomb per centimeter square. So, this is coulomb per meter square, or then you can add whatever you want. This is volt per meter, and yeah, these are the two quantities of these units, the units which you need to remember. Now, next question comes is, how do you measure the ferroelectric hysteresis loop? The measurement of hysteresis loop is essentially based upon, say, a Tower circuit who basically developed this methodology to measure the ferroelectric polarization. So, basically what happens here is, this is the circuit diagram. So, basically you have an oscilloscope to take the measurement on screen. This is the applied field, basically AC field, and what you do is that you put a ferroelectric material, ferroelectric crystal, in series with a reference capacitor, and this capacitor is essentially a linear capacitor with the, so you can say, capacitance C naught. And basically in this configuration, the voltage drop across C naught is proportional to the polarization of the crystal, and that is how you measure the polarization or the charge which is accumulated in the ferroelectric crystal, and that you take with respect to a reference capacitor. This is a very simple circuit. It can be, many people have designed equipments in their own labs based on this circuit. However, nowadays you have variety of commercialized instruments available which can not only do polarization measurements. So, you can do measurements like polarization, which is basically P versus E, You can also measure polarization versus time. You can also measure polarization versus switching cycles, and variety of these measurements are available. In order to make the measurements, sample must have, so this is your sample. So, in order to make electrical measurements, sample must have contacts. These are your electrodes, which are called as electrodes, top and bottom electrodes. Now, these electrodes should be of such a metal. Now, this is where the choice of electrode comes into picture, and which is very important, that these electrodes should not inject the charges in the ferroelectric material. Ferroelectric is an insulator. As a result, you are only measuring the short range displacement of the material, of the charges inside the material. In order to however, in order to measure any response, you need to have metal contacts, but this interface between the metal contacts and the sample is very important, and this gives rise to extraneous effects in the especially in the dielectric constant versus frequency measurement. And often, since metal has a different crystal structure as compared to ferroelectric material, this interface is of significant importance. And this, if you remember, we discussed when we module 4, the role of this interface can be taken care by making proper impedance spectroscopy measurements. However, in order to make ferroelectric measurements, remember that these typically these electrodes are made of high work function materials, like you make these, you take platinum or gold, which are basically or silver paste also in case of ceramics. So, these noble materials do not inject the charges inside the ferroelectric. As a result, the measurements are much more robust, and these measurements can be done at various times and frequencies. Typically, they are AC frequency, AC measurements, depending on the type of application, of course. So, if you are looking at, for instance, a memory kind of application, you are looking at lower frequency material, but if you are looking at microwave, then you need to go to higher frequencies, so which is in the range of gigahertz and so. So, this is how you need to make the connection, and then of course, you apply the electric field, making sure that you have a reference capacitor in series with the sample. Okay. So, this is how you make the measurements. Typically, the polarization of samples range anywhere from 5 to 100 microcoulomb per centimeter square. There is a typical value, it is not a final answer, but typically that is where the values you see. And make sure when you make the ferroelectric measurements, when you get, if you get any loop like this is not a ferroelectric loop. You should not get a banana kind of loop like this. You should always, so these are not ferroelectric loops. So, this is very important from measurements point of view. Many people, many young students who do not understand this, they often confuse with these two kind of loops as ferroelectric loops, whereas these two are not ferroelectric loops. A proper ferroelectric loop is like this. This is a proper ferroelectric loop, a properly saturated ferroelectric loop. You must get saturation here, and this should have, basically the slope should be very high. So, dP by dE at these points should be high. So, this should be as vertical as possible, and this should be as flat as possible. And unless you have this kind of saturation, this is not a ferroelectric. So, in many materials you will see that you will have this kind of material. You have this bending of the tip, and this is also because of leakiness of the sample. This is a perfect ferroelectric which is not leaky. This is an imperfect ferroelectric which has a lot of leakage inside it, and these are basically not ferroelectric materials. These could be lossy capacitors, etc. Okay. So, make sure this is your proper PE loop for a, so your benchmark is essentially this. Okay. So, the applications of ferroelectrics, they are used in variety of applications. Since you have these two states of polarization in the hysteresis loop, so you have a hysteresis loop like this. So, you have plus PR and minus PR. These two are often used as 0 and 1 state of a memory binary data storage. So, they can be used in memory devices So, materials like PZT, which is lead zirconate titanate, bismuth, Bi4 minus X, LNX, Ti3O12, which is lanthanide doped barium bismuth titanate, strontium barium tantalate, strontium bismuth tantalate. All these have been tried for memory devices, and they have been successful to some extent. The advantage of these materials is they have very high radiation resistance as well. So, they can be used in space without damaging the polarization in the space. They have large TC, so high radiation resistance, high TC, very high TC of these materials. Most of these materials have TC in the excess of 400 degrees centigrade, and they have high speed. So, they are much faster than magnetic materials, which are conventional memory materials. There are some problems in terms of integration, but if you look at the fundamental parameters, they are way superior as compared to magnetic materials. So, they are used for memory devices, and basically in memory devices the configuration is MIM configuration. So, you have metal, insulator, metal configuration. And then second application they can of course be used as actuator, sensor, etc., because each ferroelectric is always a piezoelectric and pyroelectric, as I will show in case of piezoelectric and pyroelectric material. And these memories are called as non-volatile memories. And you can see why non-volatile. Non-volatile, which means the data is not volatile, which means when you remove the field, the data is always stored. So, which means this is a good point. And since they are fast, they don't need a DRAM. Why you need a DRAM? Why do you need a DRAM in case of normal computer? Because magnetic memory is slow. So, in order to speed up the operation, you need to have a buffer memory, which is called as DRAM, which is fast memory, but DRAM is volatile. So, if you don't press Control S, you will lose the data, because if the power, especially when the power goes off, suddenly power goes off. So, you need to save the data before you switch off the power. Here you don't need to put Control S, because the material is always stored in plus PR or minus PR state at zero field. So, even if a power goes off, data remains there. So, that is why these are called as non-volatile memories. And the second application could be in camera flashes. And camera flashes is basically, so you have in this application you have a battery. So, basically a battery charges the ferroelectric capacitor. So, you charge the ferroelectric capacitor using a battery first, and when this is fully charged, you connect this ferroelectric material to a bulb, and then since this material is charged, it gives this energy to the bulb, and this bulb flashes. Now, once the bulb has used the material, bulb has used the charge, ferroelectric capacitor is discharged, you need to charge it again. So, this is what is used for camera flash applications. Again, you can see the video animation on there are animations on this side which you can go through how a flash bulb operates. And so, this is what basically is sort of the end of this part of this module on ferroelectric materials. So, essentially ferroelectric materials in summary are non-centrosymmetric polar materials, where direction of polarization can be reversed by reversing direction of light field. They undergo a transition which is called as a Curie transition. Above this Curie temperature they are paraelectric, and below this Curie temperature they are in ferroelectric state, and this is basically a phase transition. So, it can be a first order, second order transition depending upon the material, but it characterizes a change in the phase of the material or structure of the material. Typically what you call it is a material goes from a non-centrosymmetric to centrosymmetric state to a non-centrosymmetric state when you cool a material below Tc, and that is when it becomes ferroelectric. And then ferroelectric materials also have domains. These domains are regions of uniform polarization. However, because of energetics, monodomain is not stable state. As a result, you form multiple domains, and multiple domains means you need to have a domain wall, and then the balance of energy has to govern the domain size. So, that analysis we did, and we found that domain size depends upon parameters like surface energy of domain wall as well as polarization in the material, and that gives you what is called as a stable domain size. And then finally, we looked at how the domains nucleate and grow inside a material. And in ferroelectric materials, it is not consumption of unfavorably oriented domains by favorably oriented domains, they do not grow, rather what you have nucleation of new domains and the growth of those domains at the expense of any other domain. So, as a result you have domain state which is always dependent upon nucleation and growth, and that gives you the features of hysteresis curve. And since you have plus PR and minus PR state, this makes this material extremely useful technologically. And one of the most favored, one of the most fancied application is non-volatile memory, which has been tried on a few materials. It has not been commercially that successful yet, but there are promises, and the moment we get the fabrication integration of fabrication technologies right, that should be possible. So, this is the end of this lecture. In the next few lectures we will discuss pyroelectric and piezoelectric materials to finish this module off. Thank you.